So let us come to the last part of this unit, that is the part 4. Here we are going to discuss about the ion channels which are present on the cell membrane, because the cell membrane is nothing but lipid bilayer, and ions are polar. So ions cannot cross lipid bilayer. So here they are on the cell membrane. There are various uh, channels are there uh, for the movement of ions, like sodium ion, potassium ion, calcium ion, chloride ion. So they can go inside the cell, otherwise they can go outside the cell through the ion channels. These ion channels are proteins, and they are present on in the cell membrane. So we are going to discuss some these ion channels and the problems related to malfunctioning of ion channels, and the drugs which are there in the synthesis, I mean in the syllabus, targeting ion channels. Now the first is, what are the ion channels? Now ion channels are the pore-forming transmembrane proteins. As already I have told you, they are present in the cell membrane, and they are basic. Cell membrane is lipid bilayer mainly, but there are proteins are there. Ion channel also is a type of protein which is present in the cell membrane. Now they can form holes, pore channels. Through that channels, ions, sodium ion, potassium ion, calcium 2 plus ion, and the chloride ions, they can come inside the cell, otherwise they can go outside. Those are called as the ion channels. Now depending on the size diameter of the ion channels, that sodium ion, potassium ion, calcium ion, chloride ion, these all ion channels are different. They are highly specific, and ion channels are, when it is required, then only it will be in the open form. So that is called as the ion channel is open or the gate is open. But when it is present in the when it is not required, then that ion channel will remain closed. And uh, you know that these gates will be closed or gates will be opened, that is depending on the signals. Now these signals can be received by the ion channels uh, mm, mm, in two ways. One is the ligand gated ion channels, and another one is the voltage gated ion channels. Means if the ligand comes, then there will be some gate opening or closing will be there. Otherwise there will be the difference in the voltage along the cell membrane. So as a result of this disturbance in the voltage, the gate will be closed, otherwise it will be opened. So there are two types are there ion channels. One is the ligand gated ion channels, LGIC, and another one is the voltage gated ion channels, VGIC. Now let us see, this is an example pictorial representation of the ligand gated ion channel. Now this is an ion channel which is present in the cell membrane. Outside the part is called as the exterior part, and this is inside the cell. And now this picture represents that this is the ion channel is closed, and this is ligand gated ion channel, means this is the receptor. The receptor for the ligand is empty. Now when the ligand will come, means ligand is nothing but the neurotransmitter in most of the cases. So the neurotransmitter comes, then it sends the biological response, and as a result of that, the gate opens. So this is the pictorial representation of the ligand gated ion channel, when it will be open and how it will be closed. Now let us go to the move to one specific ion channel, sodium ion channel. Now sodium ion channel is present in the central nervous system. It is present in the nervous system. It is present in the brain, it is present in the heart, and it is also present in the muscles. So let us consider some medicine where the medicine, drug molecule which is targeting the sodium channel to correct the disease. So one example is the tetracaine, cane series, like the LOL series. It is now cane series, CAINE, cane series. Tetracaine is in your syllabus. Now let us see what is the synthetic scheme of tetracaine. Now, tetracaine synthesis, chemical synthesis starts from PABA, para-aminobenzoic acid. Now, when para-aminobenzoic acid undergoes a reaction with the butyl bromide, and this butyl bromide is the nucleophile. I mean, that NH2 group ki in alkylation happens. So butyl bromide is the alkylating agent. HBr goes and we get the in alkylated para amino benzoic acid. Now, when it undergoes the reaction with this one ethanol, then esterification happens, and that after means ester means OET is a better living group than OH. So in order to do that, carboxylic acid gets converted into the ester, and now that side chain which is present in the tetracaine, directly we are bringing, that is the OH, CH2, CH2, NET. So this is in presence of base, sodium ethoxide, O alkylation happens. So we get, this is, we can tell that this process is the trans esterification. Ethyl ester gets converted into the another ester. So that is the final structure of tetracaine, which is used as local anesthetic. Now, these local anesthetics act on voltage gated ion channel, means this sodium ion channel is a voltage gated ion channel which is targeted by the tetracaine. So there are three forms are there in this case, which are voltage gated ion channel. At the top we have discussed ligand gated ion channel, but now tetracaine is targeting the voltage gated ion channel, means the voltage disturbance along the cell membrane will operate the closing of the gate, otherwise the opening of the gate. So that gate, here we are considering the gate of sodium ion channel. Now we are considering three forms. One is the open form or active form, number two is the inactive form, and number three is the resting form, means it is closed but ready to open form. So the conditions of the voltage gated ion channel, here we are considering the three states. One is the active form, means the open form, another one is the inactive form, means closed form, the third one is the resting form, means closed but it is ready to open. So now this local anesthetics active on it interacts with the inactive form, means the when this voltage gated ion channel is completely closed. Now let us consider how the three interactions are happening between the cane series molecule and the active site of mm, voltage gated ion channel, sodium ion channels active. Now let us consider that is aromatic ring. Aromatic ring undergoes the pi stacking, and this is the ester C double bond O which undergoes the hydrogen bonding. Ester C double bond O is the hydrogen bond acceptor, and the active site contains the hydrogen bond donor, and the side chain we have that amino group that is protonated and that is participating in the ionic interaction with the anionic site present in the voltage gated sodium ion channel. So in this way tetracaine interacts with this and it is useful for the local anesthesia. Let us go to, so this is the membrane and this is tetracaine is coming inside and then it is binding with the uh, mm, binding site of that voltage gated ion channel, sodium ion channel. So it becomes what it is called the, so when the sodium comes it will not be open. So this is the um, pictorial representation of the how the binding happens between tetracaine and the receptor, and it is towards this thing happens towards the intracellular part, not near the extracellular part. So tetracaine on its own comes crosses the cell membrane and comes inside, and then from the intracellular part it attacks the binding site of voltage gated sodium ion channel. Now with then I will move to the calcium channel. So voltage gated sodium ion channels, um, mm, channel targeting medicine tetracaine, which is the local anesthetic that I have covered, and I am moving to the another ion channel, that is the calcium ion channel. Now this calcium ion channel, from name it is clear, this ion channel will allow the movement of the calcium 2 plus, and the important calcium channels are of voltage. Here also it is voltage gated ion channels, and the five types are there: L type, P type, N type, R type, and the T type. The first three are actually the uh, highly voltage activated, R type is the medium, and the T type is the low voltage activated. Now this is calcium 2 plus is very, we know that calcium 2 plus is very important for the biological function of our body, because it in release of number one in release of neurotransmitter from neuron, means number two is the in muscle contraction. Number three is in the blood clotting. Number four is in bone health maintenance, and in a stroke and the heart attack. Calcium 2 plus has active participation. Now we will discuss the calcium channel blocker. CCB means it is calcium channel antagonist. Like in the previous case, we have discussed the tetracaine, so which is targeting the voltage gated sodium ion channel. Now we will consider the calcium ion channel blockers, and that can be used for the heart muscle contraction, to regulate the heart muscle contraction, to treat the high BP, to stop the chest pain, mean the angina problem, to solve the angina problem, and for migraine headache. Now this calcium channel blockers usually target the L type, and the medicines targeting the L type are very well developed and they are very popular in the market. The two examples which are there in our syllabus are nifedipine and diltiazem. Now let us go to the nifedipine. Nifedipine synthesis is a very good example of multi-component reaction. Means the four components which are present in the nifedipine are combined in a single step to get the skeleton of nifedipine. So nifedipine can be synthesized in only one step by joining the four components. The four components are orthonitrophenoldihyde, methyl acetoacetate, and ammonia. Two molecules of methyl acetate. This left hand side and right hand side compounds are methyl acetoacetate. This is ammonia. This is the orthonitrophenoldihyde, and this is an example of multi-component reaction. Obviously, we need an catalyst, because and under thermal condition this condensation happens, and we get what it is called this dihydro uh, pyridine skeleton. Nifedipine has dihydropyridine skeleton. So this is a calcium channel blocker, means CCB. So it binds directly to the again inactive form of the calcium 2 plus. And for the angina patients means who get severe chest pain because of the block oxygen demand. For them, angina patients means oxygen demand is more compared to the oxygen supply, means they might be doing some, their oxygen demand is more, their body demands more oxygen, but the oxygen supply is less because of some block. So this is due to the blocked arteries. So heart becomes ischemic heart disease means it it tries to squeeze more blood so that they will have the enough oxygen, and develops the pain because they have already blocked arteries. So these calcium channel blockers decrease oxygen demand by reducing muscle contraction. Means if the muscle does not contract, then oxygen demand will come down. So in this way, by reducing oxygen demand, this they try to it tries to balance between the oxygen demand and oxygen supply by reducing oxygen demand through heart muscle relaxation. It reduces the contraction. So let us consider the pictorial representation of this. What happens? Let us see. So this is what it is called the cell membrane, and this is that calcium ion channel, and it is the voltage gated ion channel and the L type. Now, if it opens, then calcium 2 plus comes inside the cell, and calcium 2 plus undergoes a cal- calmodulin complex. With calmodulin, it undergoes the calcium calmodulin complex. And by the time this already, you know, this reaction, myosin is a protein, so it has a light chain, means lightweight chain, peptide chain, that in presence of kinase undergoes the phosphorylation, and that phosphorylated myosin interacts with the actin in presence of, by looking at calcium 2 plus calmodulin complex, this kinase um, catalyzes this phosphorylation, and then phosphorylated myosin interacts with the actin to give the actinomycin complex, and that leads to the contraction. So this is normally happens. Now if in presence of that ischemic heart disease patient, otherwise angina patient, for whom we doctors are trying to reduce oxygen demand, they will be on calcium channel blockers, as for example nifedipine. So in that case, what will happen, this L type voltage gated calcium ion channel will not open, so that the series of reactions which is leading to mm, cardiac muscle contraction will not happen. So heart will not pump more blood, and so therefore oxygen supply will be less, because the oxygen demand is also less, because for and in presence of CCB, there will be reduced cardiac muscle contraction. Now we will go to the another this thing, molecule, medicine, drug, diltiazem, which also targets the calcium 2 plus ion channel. So let us consider that is the um, orthonitrothiophene, and this is a complex, this is an epoxide ring, that is a benzene ring, and attached with the what it is called the epoxide ring. This is the 1,2 disubstituted vicinal disubstituted epoxide ring, where the sulfur will act as a nucleophile, and the ring opening will take place. So the ring opening will take place in the, this is an this position, because this position is more positive because of the benzylic position, as well as it is a, because of this electron withdrawing group. So this position will attack, and the OH will go to the mm, alpha position of ester group. So we will get this uh, 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 compound after nucleophilic ring opening by the orthonitrophenol. Now we know that this compound contains two chiral centers, and the two chiral centers are of different types. Means this comes under AB type. To total 4 stereoisomers are possible. 3O2 isomers are there. Erythro 2 isomers are there. So 2 plus 2 is equal to 4. But we have to go for the separation because diltiazem is one chiral drug. So hydrolysis means that ester group will undergo the carboxylic acid, and then we can consider it as a racemic mixture of carboxylic acid, which can be separated by using optically pure chiral base. So the next one we have to proceed with the only one enantiomer out of the four, so that is the SS compound. So this center is also S, this center is also S. That will be uh, mm, proceeding for the final synthesis of diltiazem. Now, when it is subjected to the reduction, then here reducible group nitro will be converted into the NH2, and this NH2 and the carboxylic acid will undergo the cyclodehydration, means water molecule will go, and we will get one ring. That is middle ring is a seven-membered ring. So lactam formation has happened, and we got the seven-membered ring. Now it is subjected to the acetylation. So the acetylation means usually nitrogen and oxygen both are there, means nitrogen will be acetylated, but this nitrogen is a part of amide, so therefore secondary, I mean this secondary alcoholic OH will become the acetylated, and after that what will happen, that chain will come, and this in alkylation will happen. So with this NMe2 CH2CH2Cl will come, and ACl will go, in alkylation will happen, and so this is what it is called the diltiazem, which contains the benzothiazepine ring, means is a seven-membered ring which contains the sulfur and the nitrogen. So it is a type of benzothiazepine class of calcium channel blocker. Now let us see what happens actually here. So this is calcium channel. So this is calcium channel. In this picture it is that open, and the calcium 2 plus is coming. Now this is, it has gone to the inactive state. Inactive state means it is completely closed, and then what it is called the, and after inactive state it will go to the resting means it is closed but it is ready to open. So this state, this is the state, the time between the inactive state and the resting state, resting stage, these two stages it will be delayed by diltiazem. It is not like nifedipine, that is also calcium channel blocker. Diltiazem is also calcium channel blocker, but their mode of actions are different. Diltiazem mode of action is, so let us say that this is what it is called the another molecule. So with this we have finished the calcium 2 plus ion channel, and sodium plus we have completed, calcium also we have completed. Sodium channel targeting one drug molecule is there, that is tetracaine, and the calcium channel targeting molecules are there, two are there, nifedipine and diltiazem. Now we will go to the potassium ion channel targeting molecule, that is the 4-aminopyridine. I mean, it is in short form called 4AP. So this is pyridine nucleus की fourth position in H2 group is there. So it also blocks the voltage gated potassium channel, and it is used to treat the multiple sclerosis, a disease where the myelin sheath of nerve cells are damaged. So you know the nerve cells, in this chapter beginning only we have discussed that pictorial representation of neuron, that is the nerve cell is nothing but neuron, and when the message goes in the form of the electrical impulse through the action to maintain the intensity of the signal, action is coated by myelin sheath. Now this is sclerosis is the damage of the myelin sheath, and I hope you know that nerve cells, our body does not know how to repair the damage related to the nerve cells. So these all lead to the neurological disorders. By giving medicines only we can delay the damage, but we can't repair those damages. That is the problem of our mm, damages targeting the nerve cells. So uh, neurological disorders, basically we do not have cure. By giving the medicines, doctor prolong this, actually that is the decay will be slow, that's it. So now you see that how to prepare the 4-aminopyridine. So pyridine 2 carboxylic acid we have to take, because we have to block the second position in order to introduce the NH2 group at the fourth position. So after this pyridine 2 carboxylic acid, when it is subjected to the Chichi-Babin reaction, sodium amide in liquid ammonia, NH2 group will go to the para position because the ortho position is blocked, and now it will undergo the thermal decarboxylation. Simply by this carboxylic acid will be activated because of the adjacent nitrogen. So we do not need any decarboxylating agent like soda, lime, etc., calcium hydroxide, sodium oxide mixture like that. It is not required. It is thermal decarboxylation. By heating, the carbon dioxide will go from the second position and we will land up into the 4-aminopyridine. So now this is what it is called. The in our body many potassium channels are there. It blocks the it means that is 4-aminopyridine blocks the voltage gated ion channels of potassium ion, and prolongs the action potential and increases the neurotransmitter release at the neuromuscular junction. So it prolongs the action potential and increases neurotransmitter release at the, all these things previously we have discussed, that neurotransmitters are able to send the message through the synaptic gap. Now there are four types of potassium channels are there, like that voltage gated ion channel, calcium 2 plus mediated potassium channel, G protein coupled receptor associated potassium channel, and the Lick channel. Now these what are the functions? Now, these potassium channels set resting potential in many neurons. Now what do you mean by resting potentials? All we will discuss later. That you see that they shape the action, but these are all terms related to the how the electrical impulse happens. Neurons send the message in the form of the electrical impulse. So resting potential, action potentials, these are all related to that only. So we will discuss all these things. So this is what it is called the these are happen. So any malfunctioning may lead to the arrhythmia, means it is not in rhythm. Suppose heartbeat is not in rhythm, so this is not arrhythmic. So arrhythmia, to put it in order, doctors will give the anti-arrhythmic, means to set right it. Now, potassium channel also regulates the secretion of the hormones, as for example, insulin. Yesterday we have discussed estrogen is one hormone. Insulin, like this, insulin is also one hormone, which imbalance of this hormone leads to the diabetes. Now, let us see what do you mean by resting potential, what do you mean by action potential. Now, the resting potential means when neurons take rest, that is minus 70 millivolt. So inside more potassium and the outside more sodium ion gets accumulated. So that is minus 70 millivolt, and at that time neurons take rest. So minus 70 millivolt is the resting potential. Now action potential. Now when the neuron sends information from the dendrite to the axon, then it is created by depolarizing current. Now the depolarization goes to minus 35 millivolt, then neuron fires action potential. So here we have written in this picture A, B, C, D. So what is A, what is B, what is C, and what is, this is actually that electrical impulse. When the message will go, information will go, signal will go inside. It is not outside the neuron, it is inside the neuron how it is coming. This is A, B, C, D. A is the sodium channel opens, and B is the, more that activity will be there. C, B, it is little up. B, more activity will be there. Now C, when it goes up, then sodium channel closes and the potassium channel opens. And then D is the potassium channel closes. So this is highly regulated by voltage because it is a voltage gated. We are discussing voltage gated potassium channel. So action potential, resting potential is minus 70 millivolt. Now when it is uh, that is called as a resting potential. And action potential means when neuron sends information from dendrite to the axon, it is created by the depolarizing current. Now when depolarization goes to the minus 35 millivolt, then neuron fires the action potential, means action starts. Now see, this part is called as the, this is, see here, minus 70 millivolt key, it is, this is 0, that side is the positive side, this side is the negative side, and this is the minus 70 millivolt, that is, it is, if it is continuing at the minus 70, so it is called as a resting potential. Now it is a B part. B part is the minus 70, it is increasing to the minus 55, and then you will be having the, it is going to the highest value. So this part is the depolarization. Go to the previous. So this is what it is called, the minus 55 milli. When the depolarization goes to the minus 55, neuron fires action potential. So when it is going to the minus 55, then action potential it will go up. So this type minus 55 to plus 30, it is called as the depolarization, it is going up. Now it is falling. So falling is called as the repolarization. This part is called as the repolarization, and minus 35 it is, minus 55 it is reaching. So it is threshold. So now this is what it is called, the, it is coming down, even it is minus 70 key, it is dropping. So that is called as the hyperpolarization. So this is, so this is the minus 70, minus 55 plus 30, it is dropping, and it is dropping below minus 70, that is called as the hyperpolarization. So the types of ions which are participating, it can be the potassium and chloride, or it can be the organic anion, it is the sodium ion, and that is a big size, means what I have written in the big size means inside the potassium ion concentration is more, and the outside the sodium concentration is more, that is resting potential. I have already written in the previous slide. Inside more potassium is there and the outside more sodium is there. That is the resting potential. So this is the resting potential inside. This is the inside the cell. Big size means potassium concentration is more, outside key sodium and the chloride key concentration is more, outside potassium concentration is less, inside sodium and the chloride concentration is less. Now you see that this is damaged actually. Here you see, this is actually that is that action, and outside you will be having the myelin sheath, but the myelin sheath is not there here. So this is the damaged myelin sheath is damaged. So here the action potential moves very slowly compared to the the action which has the myelin sheath cover. So this is like this. So this is, it moves very slowly. Action potential moves very slowly here, means it is damaged. It has to go to, na, that is plus 30, but it is not moving. It is not going up to that. So yeah, in this condition, doctor will give the 4-aminopyridine. So it will do the same work as if it is, there is no damage. So 4-aminopyridine blocks the potassium channel and increase the conduction of action potential through demyelinated action. So with this we have finished this unit also. Thank you very much.